All right, so like about 10 seconds has passed, but now we can get up. So that's just kind of a commentary on those. Now, we've done a bunch of stuff on how to calculate these. I mentioned that Newton has his own thing that goes on here. And Newton's addition is actually a fairly small addition that goes in, but it's a fairly nice addition. Where, again, a lot of these ones add properties we want. That's it. You know, I mentioned a bit ago that, you know, Chebyshev's interpolation, he gets a set of basis functions, different than just the monomials and things like that, because he's trying to get functions that have more sampling points to the outside so that he can reduce the errors on the outside where the overshoot goes. Well, Newton had a different problem that he wanted to solve. Imagine I went through and I considered a function that kind of looked like this. Well, actually, let me just do we'll do a very small problem. All right, so let's assume I'm trying to fit x, y points. And I'm going to write this in matrix. Here's my ax equals b, right? So, you know, I'm going to try, this is a constant. So I'm trying to find the best constant function that will account for y0. Well, trivially, I'll find a0 equals y0, right? And, you know, that's just taking this and saying, you know, I originally had x0 and y0, and I just fit that straight line to account for that point. Now, let's say I found out that this was actually a line coming some direction. I get a second point that comes in. So I get x1, y1. I don't want to recalculate a0. I would like to just now keep my old a0 and add in an offset that will then allow me to now fit a function through there. Right? Without recalculating anything of what was before. I just add the new details. Now if you think about it, to get this, all I'd have to do is, if I took this function and I added the constant to it, I would get that line. So I just need to get something that puts a 0 at that point on a line. Well, if you go back to, you know, our earlier one that went on, we know that was the u functions, right? So if I took the thing x minus x0, that's got a 0 right there. And if I took that and multiplied it by some a1, boom, there's my answer. So I can take this and say, well, taking that function, it still has the constant 1 because I kept it. And now I've got this whole thing. I've got my x minus x0 as my point, but I'm going to calculate this at x1. Right? So that's my x minus x0, and this is a0, a1. And now I've got 2 points, y0, y1. Well, if you did forward substitution, you would still find that a0 has to equal y0. And then that one would come in. I'd get y0, and then I get this, and I can solve for my a1 because these are known, that's known, so the only unknown is a1. So boom, I can solve it using forward substitution. You already have a forward substitution routine. It'd be easy to do this. So now I've got a linear function. Another point comes in. I realize, oh my goodness, it's a quadratic. But I don't want to recalculate everything I've already done. I would like to just add in my extra new function. So I'd like to have this. I'd like to keep my first calculated one, and I'd like to keep my second right? So I calculated x1 and x2 now. Now I don't want to mess those, so to avoid having whatever I calculate later mess those up, I've just put zeros above. And now I add in a new thing. Now I need something that's not going to affect either of these 2 points. So it must be 0 at both of them. So in order to do that, I need x minus x0, and it has to multiply x minus x1. This quadratic is 0 at those 2 points. That gives me these 2 zeros. But I want to calculate this one at x2, my new point. So that's times a0, a1, a2, and has to equal y0, y1, y2. But I've already calculated these two. I know what they are from my earlier steps. So I can just already take those, stick them in there. It's guaranteed to fit. And this last equation will tell me how to calculate the next a2. And it's all because of this lower triangular. Since the upper triangle is all 0, there's no influence of later equations on earlier equations. So that allows me to just keep building as it goes on. So this is kind of a nice feature because a lot of us get into something and we calculate something and we go, oh man, it was just a little too small in the order. And because the order of my polynomial is too small, I need to calculate something new. Right? And so this allows me to now, it's a nice format for them. I get reasonable polynomial functions that interpolate into them, and I can actually just keep building them. You want a higher order? I leverage it. I get you a higher order. So there are actually in a lot of even fancier functions ones that go through and do the same thing. Right? Because this is a nice feature. Right? So if you go into filtering theory, we actually have filters that talk about how do you keep increasing the order, right? Because this is going from constant, linear, quadratic, cubic, quintic, right? So I can keep going on quartic, quintic, so on and so forth. So I'm updating the order. Well, we have order updating filters that go to higher order filters that go on. And the higher order filters that go in are just, right, this is increasing time. As you add new columns, you're increasing the order. Right, more coefficients that go in. So as you keep increasing the number of columns, that's an order update to the filter. I could do the same thing in interpolation. Now, Newton's, because he uses this nice lower triangular format, gives you a great way to solve that. So that's the thing that I think is worthwhile about Newton's as it goes in. Most books just start up and they go, look, it's lower triangular, so that means it's independent of any earlier thing, just solve it for its substitution. Completely correct, but I think it makes a little more sense if you kind of walk through what are you trying to do and how it builds it. And while Newton didn't formulate it with this, he did formulate it with increasing equations. Matrix notation didn't exist at that point. All right. So do we feel good with these? There's one last little thing I need to do. Watch my time so we don't get... Okay, so I'm almost out of time. So let me just kind of mention this last topic really quickly. And believe it or not, it's actually just like this. I think it's pretty straightforward, right? Because all I had to do there, those equations I was setting up, is the equations that you're just going to enter. You've got those matrices, you just write that inside MATLAB, right? A equals and B equals, and then you've got your coefficients x equals A backslash B. You've now got x in MATLAB. So it's like a 3-line program. And now you can stick it back in and interpolate anything you want. So MATLAB allows you to do this stuff very, very quickly. This is where we joke MATLAB allows you to make errors fast. Because you can go in and you can try these different things, and depending on which one you do, it's either a good idea or a bad idea. But you can try it, you can find out what doesn't work, and move on to what does. Okay, so the last one is to get into the idea of splines and cubic splines. Right, so I'm going to just kind of jump to cubic splines and set up the idea behind what's going on here. And you'll notice it's not actually that tough of a deal. Imagine now I've got my series of points that are going in, and on any one of these intervals that's in here, what I'm going to do is I'm going to do these piecewise, and I'm going to have a cubic spline for each one. Right? So this one will be, cubic spline 0. This will be cubic spline 1. This will be cubic spline 2. Right? So I have all these little cubic spline sections. And what I want to do is I'm going to want, at these boundary points, All right, so actually I make this x0, x1, x2, x3. So cubic spline 0 is only going to be defined between x0 and x1. Cubic spline 1 only between 1 and 2. Cubic spline 2 between 2 and 3. Now what I would like is I don't want them to look like this at a point. I don't want this continuity. So I'm going to require that cubic spline 0 at x1 has to equal cubic spline 1 at x1. Okay? That will avoid the discontinuity jump that's going on. Similar for each of the other ones. Right? So that means cubic spline 1 at x2 must equal cubic spline 2 at x2. So I'm just going to look at cubic spline 1, kind of a middle point here. But I'd also like it to be smooth. I really don't want one spline to come into a point and the other one to come off, right? You get this kind of funny little point. So to avoid that, or to get the smoothness property, I want the derivatives to match. So that means cubic spline 0's derivative at x1 must equal cubic spline 1's derivative at x1. And cubic spline 1's derivative at x2 must equal cubic spline 2's derivative at x2. Now if you think about it, I now have 4 equations. 4 equations can solve for 4 unknowns. Right? 4 equations, 4 unknowns. That means I can have up to 4 unknowns inside C1 and solve for them. Because I did this for C1. Right? I could have rewritten these equations for C0 for whatever else. So you'll get, right, these are the 4 ones here. That's why it's a cubic. Because a cubic gives you the constant, the linear, the square, and the cube. That's 4 terms. You need coefficients for each one. So I've got 4 unknowns, the values of those coefficients, and I've got 4 equations to solve for them. That's why you don't go higher. Okay? And you get that for each one, so you get a large matrix, or you can kind of solve them in chunks. That's going in. Now, these are then rewritten, because I can take my functions, and there's a lot of ways you can do them. You can write your cubic splines, right, C1 at x. I can write in this kind of a term. I can write it as, right, A3, 1, x3 plus A2, 1, x2 plus A1, 1, x plus A0, 1. Right? I could make that my cubic spline. And then for each one of these, right, I could just take that and I could stick it in. Right? As we're going through, I can take it, I can take its derivative, and away we go. Now, there's nothing wrong, you can fully develop these. So this is just a note on the proofs for these. What we will often do to simplify things is we'll rewrite these ones in terms of, right, hitting like an x minus x1 or x minus x2. Because then it goes to 0 at that point on there. And write them in terms of functions on those. When you multiply them out, you would get these. But then when I'm actually go to one side or the other, a bunch of stuff just drops to 0. It just simplifies my calculations. Since all you're doing is proving how to get them and massaging the form of the equation, right? It just changes the matrix form. That's the whole trick to it, right? So you'll often see people rewrite these into different forms. A very common one being rewriting this one into stuff that looks like, you know, x minus x1 cubed or something that's going in. And you'll get these, and you'll still get x cubed term. But when you hit on the x1 side over here and you stick it in, boom, that whole thing flips away. All right, so it's kind of nice to write them. You know, you could do that, and you could also get the, you know, x minus x2 cubed. If you really want, you can handle both sides. Right, so there's a lot of ways you can kind of combine them to simplify your life up. That's going in. So I just kind of mentioned that as a side thing. Sometimes we'll add extra stuff in just because it makes our life easier to prove stuff. Now, the resulting thing, if you were to multiply these all out and swamp them, you could rearrange them into this form. So hopefully that makes sense. Now, if you consider these that go on, I've made the claim to you, right, by showing here that I've got 4 equations, 4 unknowns, boom, it works. Right? The only time you run into a problem is here. When you get to the outside edges, I've got 2 equations to match here. One, the point you're trying to fit, the other to be consistent slope of the outside. And then you've got a point here. Right? So I end up with 1, 2, 3. So on the outer edge, I'm down 1. And I'm down 1 here. All right, so that leaves me a total of 2 unknowns on the outside edge that's under. So this gives you the type of splines. All right, because I've got to give you those last 2 pieces of information. I can give you a starting slope. Right? I could give you a free end. Right? That it wants the minimum bending inside here that's going in. Right? I could make it such that there's one more segment that loops around between the last 2, and then they're all interior that goes on. So there's a lot of these extra. You'll see tons and tons of different types of splines that do all kinds of extra stuff. It's all because you've got these ends here where there's 2 unspecified pieces of information. So you've got more unknowns than equations. So now you have to pick 2 more equations. Well, what 2 equations you pick really kind of has to fit your problem. And so since there's nothing that forces it always to be one versus another, you're free to pick wherever it wants. If you then just take these, write them into matrix format, just like we've written all the other ones into matrix format, you get the how to solve for a cubic spline. And boom, you're done. Now, splines, if you notice each one of these, I've got them on a little finite basis area where they go in. That's the same thing goes in. When you go to B splines, go in, they just have a basis function section, right? In between 2 points, the first basis function is a square, so if I've got, here's my x0, this is x1, x2, x3. The first basis function is just a 1, and it will repeat, right? There'll be a basis function for each one of the intervals. That's the constant term, 1 for each interval, just like with my C-splines. And then the next one will look like, this is sometimes called the hat. It's a straight line up, same line coming right back down, and it's 0 elsewhere. And then for the next area, same thing that goes on. Again, you have that question of should I loop it, because there's that little extra bit here and over there to fill them in. But if you add these together, this adds up to a constant 1. If I were to loop this last function around and make one that comes here and comes down, right? So it loops all the way around, and you added all these up, it would be a constant 1 everywhere. Right? So that's kind of the goal of what's going on to each one of these. That's the normalized part of it. You go to the square, it's just a quadratic, following the same thing, except that one now goes across, and you get this kind of, it looks like a bell curve. Right? All right, so that's, and then shifted by 1 each time. So that's the B curve, or B splines that go in. So, I'm not trying to, again, give you a finite or ultimate answer on everything to calculate about this. The book actually goes through how to get these. It's actually pretty trivial. Each one is built on the next. You just take this one, multiply it by the constant term, and then 1 minus that gives you the second side. And they just built each one off. That's actually where each one comes in as it's shifted down. And they just build, so you get all the first ones here, and then these ones are just built from the function t times that, or x times that. Right? So x times this gives me this side, 1 minus x times this gives me this side. X times this one gives me here, 1 minus x times that gives me this. So, yeah. And then this one is built up from this, x times this, 1 minus x times that. Right? So you just keep building them up by taking another x times the previous step and 1 minus the shifted. And you just keep building and building, they'll get wider and wider, and which gives you the smoother fitting across everything that characterizes. But that's splines. If you take this same idea and you now fit it to weird, funky functions, you get wavelets. Same idea. Right? You pick a particular basis that's recursively self-similar, but who cares? Right? Instead, this one's different at each stage. That one's recursively self-similar. But again, you know, you're trying to fit a certain set of basis functions to them. So worth looking at least on those. I'm hitting that one really lightly because I don't need it for the fall. So I'm just kind of mentioning it because people do hit it in other areas. So I think at least knowing where the terms fit in is important. But I don't need it, so I'm skipping it, other than to give you a little lead in. I think it is worth looking at, right, just for roundness of education, but you know, not necessary for our immediate future. The C-splines are a little more important, which is why I went a little more detail into them, because that is something we do. It's very quick and easy to calculate, and therefore it's helpful when we're like fitting like a proton path and that. We can pick certain points and interpolate between them, and C-splines are good enough for that. So anyway, hopefully that helps.